Welcome to this section of the course. In this chapter, we'll be covering vectors. In particular, we'll look at coordinate system in three dimensions. We'll look into vectors in three dimensions. Then we will look at solving geometric problems in three dimensions. And finally, we'll look at applications of vectors in mechanics. So, the first chapter, or first exercise, will consider three-dimensional vectors, and the length of three-dimensional vectors is found by Pythagorean theorem. Just a tiny proof before we go any further is that if we have to find the length of O to A here, given that A is here, absolute sign here is measuring the magnitude of the vector. The word magnitude simply means the length of the vector in whatever units that the x and y coordinates are measured in. So why and how is this coming that we are sticking three dimensions under the square root? Well, if we had to figure out the length of O to this point, let's say B, O to B would be measured with square root of x squared plus y squared, because the B is in the plane of x and y. Then we need to consider the length of B, and we need to square it and add it to B to A. Right, B to A is simply Z. That means that now we need to square OB, and that means OB squared is going to be the square of the square root of x squared and y squared under the square root. Therefore, this square and the square root cancel away. And we said we need to add z squared to that to find the length of OA. Now, the OA here is going to be square. That's going to give us the square of OA. Therefore, we have z plus x squared plus y squared to be OA squared. To find OA, an absolute value of OA, we need to take the square root of x squared, y squared, and z squared all added together. Okay, so that's the preliminary. We can drop the O, and the magnitude of A is therefore what this is. Okay, so let's look at the first example here. We've been told that point P lies at point 4, 2, and 5 in the three-dimensional space. That means that it's somewhere in the three-dimensional space here. You don't have to sketch this accurately, but this is just an estimate. So the question is asking us to find the distance from the origin to the point P. All we have to do is take those numbers and put them into the formula, and we will get an answer of 6.71 to two decimal places. Right, in this next example, we've been told that the Cartesian system is used to define the coordinate system, by the way, in three dimensions. So we've been told to find the distance of point A to point B. Now I've put this on an estimated diagram. This is not accurate by any means, but it's just a way to provide you with some what's happening. Point A is, if point A is here, we can represent the position vector. That means the vector that's pointing from the origin to the point A is called position vector, by this blue arrow here that I'm labeling A. Okay, so this is A. And for the position vector B is this second arrow, blue arrow. If we want to travel from point A to capital point B, and by capital B to capital B, we have to travel backwards on the vector A and forwards on vector B. Therefore, we have to subtract the position vector A from position vector B. Therefore, we write position vector B to be positive first as 8, 6, and minus 5 in a column vector, and we're subtracting those values from each other. It's simple maths, and I'm not going to explain how you do simple maths, but that's the final answer. So, this is the definition of vector A to B. Don't forget we were asked to calculate the distance between A to B. What's the final step of the work? Of course, we will apply Pythagoras in 3 dimensions. We will take the absolute value or find the magnitude of A to B. Final answer is 11.8 units to the 1 decimal place. Now, in this third example, we've been given the coordinate of A, but coordinate of B has one of its components missing. We've labeled it K, or rather the question is labeled it K, and it has told us that the length of vector A to B is 3 units. So on this three-dimensional, this sketch is by no means accurate, but it's just showing you that there are two possibilities, or more than one possibility, where the length from A to B is equidistant. So this disk here is showing you an equidistance where only the dimension z is changed. Because we have to fix dimensions x and y, therefore there is only two possible values. How can we do this? Well, we're going to take the absolute sign or the magnitude, that is 3 units, and work backwards from it. We're going to build the formula in reverse. We know how to find the vector A to B, just like we did in the previous example. So first of all, we subtract vector A from vector B. That is, position vector A here is subtracted from position vector B. What we end up with is this column vector here. The magnitude of column vector A to B has to be 3. Therefore, we need to take these values and put them under the square root, square them before we put them under the square root. So we'll have -1 square plus 2 square plus k minus 3 square. Now this should equal to 3. To solve for k, we simply square both sides. So we'll have 1 plus 4 plus k minus 3 square to be equal to 9. We can take 1 and 4 to the side and expand the bracket at the same time. So we'll have these values. So taking 5 away from 9, we will have 4 there. Then we can bring that 4 to one side and actually have this as a quadratic that's equal to 0. Therefore, now we have 9 minus 4, which is 5. This is easily factorizable. We can see that one of the factors is k minus 5 and the other factor is k minus 1. Now we know that possible values of k are either 5 or 1. Okay, so let's look at the next example.